Welcome everyone to another episode of Vision Basic. This video is going to be full of character. That's right, we're going to be talking about, well, characters. You know, those little things that run 40 columns across the C64 screen and 24 rows down? And we're not going to talk about just any characters. We're going to be talking about the kind you design yourself. Most of the games you play have a redefined character set. You could use the existing graphic symbols in your games, and they may work fairly well, but at some point you're going to want something more. If you go back in a time machine to the 1980s, you might stumble upon a young lad scribbling out character shapes on graph paper while sitting at the kitchen table. That's just the way it was back then for a lot of us. You might have had a program on the computer to make the task simpler, but a lot of us were using graph paper. We did a lot of things on graph paper.
And that's the way it was, and we liked it.
To design a high-res character, you need to section off a grid comprised of 8 pixels wide by 8 pixels tall. You'll see a grid on screen that's similar to what one would draw on the graph paper. At the top of each row, you would write values that are powers of 2, starting from the right and increasing in value as you go left. Honestly, I can't understand why the values increase as they go further left, because from a positional standpoint, it makes more sense for them to decrease. But I suppose the designers of the graphics chip thought more along the lines of how we format numbers themselves. For example, the tens place is left of the ones place, and the hundreds place is left of the tens place, and so on. Who knows? By the way, I'm going to get to creating character shapes in Vision Basic, but some of y'all might want to experience a little nostalgia. And those who are new to the C64 should really learn this stuff instead of just relying on modern tools for everything. Also, I'll tell you how to find a character set editor in the video description to help simplify the process of more extensive character set redefinitions. Before we get to creating characters in Vision Basic, we're going to start with the regular Commodore 64 BASIC. Okay, so next you would draw the shape you wanted to create within that little grid. For old fuzzy CRT screens, it was best habit to place at least 2 pixels side by side so that you can actually see the pixels. A single pixel by itself or a vertical stripe of single pixels might appear almost invisible against a background or other nearby pixels of other colors. For this example, I'm going to make a tongue. Why not? It's my character and I'm going to do what I want. So here we have a tongue. The next step is to add up the values for every pixel that has been filled in or turned on. By the way, turning on a pixel is not as fun as it sounds. They just kind of sit there. No noise, no fanfare. So we go row by row and add up only the values that appear over pixels that have been turned on. And then we place the results off to the side. These are the values we will poke into the appropriate place in memory. So what is this appropriate place in memory? Well, that's complicated. For starters, all of your sprite, character, and screen data need to reside within a single 16K bank of C64 memory. That's just how it works. And your sprite data cannot overlap your character data, and your character data cannot overlap your screen data, and your screen data cannot overlap any other important data like your program, for example. Many inexperienced programmers try to cram everything within the first bank of memory, which runs from 0 to 16383. They soon discover that their program may outgrow the space, and many discover the hard way that their character or sprite data might become corrupted by being overwritten by variable, array, or string data. Or even worse, the program itself may become corrupted. Now you can lower the top of basic memory to help prevent such corruption with the following pokes. Oops, 52. These pokes will help to contain your program and variable data to the area that runs from 2048 to 14335. The lower limit of 2048 is the normal start of basic RAM, but the pokes take care of the upper limit. Just take the 56 that you see here and multiply it by the magic value of 256 and you get a value of 14336. And this is the starting point for our character data, 14336. But now the program will be seriously boxed in to an area that it can easily outgrow. Some people try to move the start of basic RAM instead and place it above all the sprite and character data, but the program itself cannot move the start of basic RAM. You usually need to whip up a loader that can help set things up. So why bother with any of that? Let's just move everything higher up in memory and out of the way. The only caveat is that we will also need to move the text screen. Honestly speaking, one of the best places to put a character set is in the third and final bank of C64 memory, which runs from 49152 to 65535. Here, you could place a text screen, a redefined character set, some machine language routines, and a decent amount of sprite shapes, and none of this will interfere with your basic program in basic RAM. Even if you're a beginner, I implore you to download a decent memory map for the Commodore 64. I highly recommend mapping the Commodore 64, which can be found at the website archive.org. This book can help you tremendously, especially in figuring out where to put all of your data, like sprite and character data, or even machine language programs. Okay, so if you look at the simplified memory map of the C64 memory on screen for Video Bank 3, you will see that we have a bird's eye view on where to place things. There is free RAM that runs from location 53248 to 57343 that can be used for character sets and sprite data, but it's difficult to utilize from BASIC. So I'm going to pick screen 49 for my text screen, and I'll place my character set at character slot 25. And we'll have about 1K of RAM left free for machine language routines to span from locations 49152 to 51199. And we could place up to 128 sprite shapes from location 57344 to 65535. I'm not going to make an actual game or program in this video. I'm really just giving you a layout I might consider if I were to make a game. A couple things need to be noted here. Our screen will reside at locations 50176 to 51175, so it will no longer reside at the usual 1024 to 2023. So the sprite shape pointers will also be in this area at the very end of the 1K region, at locations 51192 to 51199. And I'll jot those down for you if you want to write them down. So, oops. 51199. The sprite shape pointers are always at the end of the screen's 1K area, within the last 8 bytes of it. For beginners wanting to toy around with sprite shapes, keep this in mind. Another thing to point out is that you cannot place the text screen under the kernel ROM that runs from 57344 to 65535. You technically could, but such a screen won't function properly if you plan to use print statements to dress it up with. So you can put character data there and sprite shapes, but I say to avoid putting a text screen there. You also can't readily read the data in the RAM that's under the kernel ROM, but you can certainly stash data there. If you do place sprite shapes under the kernel ROM, they will be numbered with values from 128 to 255. Okay, so now that we know where we're going to put things, let's start typing the code that will make it happen. First, we should make a copy of the original character set to our chosen location. We'll need to disable interrupts and expose the character ROM. So here is how we accomplish this. And I'm just going to have it insert. And there you go. This line here disables interrupts, and this line here exposes the character ROM. And now we need to copy the exposed data with this line. Boom. Now, as you can see here, we have a lot of addition going on here. So for better speed, we can change it to this. And in the process, we are eliminating one of the math functions here. You can also elect to copy the lowercase character set if you wish by copying the data from locations 55296 to 57343 instead of 53248 to 55295. Anyhow, just change line 30 to this. Now, I don't want to switch, well, heck, why not? Let's just go ahead and we'll copy the lowercase character set so you can see that it actually works. Now, this is a slow process in BASIC, so it will take a few seconds to make a copy. You might need to warn your the person using your program with the usual line of please wait a minute, or not a minute, but a couple seconds. Finally, we have to put some registers back to their normal values with the following pokes. Before running this code, it's crucial that you type everything in correctly, or you'll probably crash your computer and have to start all over. So this is a bit of code you'll want to get out of the way immediately before going on to make the rest of your program. Okay, so now we need to tell the C64 where to put our screen and where to find our character set. So we need the following pokes. First, we need to switch to Video Bank 3, so the following poke will do that. And here we have BA for bank, representing bank 3. And this little formula here will change the video bank to 3. To bank 3. Next, we can set the screen location and character set location with the following poke. Finally, we need to tell BASIC where to print stuff at. So we do this with the following poke. Now there are two parts to moving the screen. The first is by actually telling the computer where the screen is at, but also where to print things to. Those are two separate things. Just keep that in mind. Just because you move the screen does not mean that BASIC is going to automatically start printing stuff over there. Now, all of these registers are explained in great detail in Mapping the Commodore 64, so please refer to the book for a better understanding on how they work. Let's run the program and see what happens. The one issue with this last poke is that when you press stop and restore together, you won't be able to see your cursor when the text screen is moved back to location 1024. And now, believe it or not, as you can see here, we are actually on our new text screen, both printing and displaying, and in lowercase. This screen is no longer at 1024. This screen is at 50176. Okay, so let's try to go back to our regular text screen. And there you see, no cursor. This is the downside of moving the text screen, mainly the downside of moving the location that tells where to print stuff, location 648. So we'll have to type the following blindly. You might want to press the clear screen combo first. And keep in mind I'm typing this blindly, POKE 648, 4. And there you go. We got our cursor back, and we need to make it white, so that people don't complain. Anyhow, now you can see that our cursor has returned to us. Hello, little guy. We missed you, albeit briefly. Now, if you want to make it easier to get back to the regular text screen, you can put a line like this in your program. And you can put a block in front of it, like so. And what I mean by block is you don't want the line to be run as part of the program. You want to just kind of call it up whenever needed. And then just run line 1000 anytime you need to go back to the regular text screen. Like so. See? It works. Actually, there's no real way to test it here on this because we're back at the regular screen. One other thing I need to point out is that when you switch back and forth between text screens, the screen line link table can get messed up for the screen you wish to edit your program on. So if you go back to the regular text screen at 1024, you might press return over an existing line that is greater than 40 characters, only to find out that the second half of your line might be missing when you go to list your program. I say this from experience. Okay, so let's at least show you how to create a new character using the data from earlier, our little tongue character. We'll type in a data line, or more precisely, I'm going to insert it. That's our data. And we'll read it into memory. But first we need to decide which character we are going to replace. Let's go with the asterisk character. The asterisk character is poke code 42, so its position within the character set data would be calculated like this. 51200 is where the character data starts, and each character takes up 8 bytes within that data. So we multiply the poke code by 8 and then add it to 51200. Now we just need to read the new character data and plug it into memory. And now we can run the program. And remember what it's doing right now, copying the character set. All right. And if we list our program, we'll see that every asterisk has been turned into a tone character. Right here, 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 and here. They kind of look like little tongue devils, but that's supposed to be a smile at the top of the tongue. The tongue is just poking out of a mouth. Don't judge my art skills, okay, bruh? And now we are going to use our little line 1000 here to bring things back to the regular text screen, and our redefined character will vanish. All right. Now, something you can do at this point is to clean up some of the pokes in the program. A lot of the pokes look messy because they attempt to either show which bits are being manipulated or because we want them to remain versatile. And, A&D, is used to turn off certain bits, and OR is used to turn bits on, in these pokes anyhow. See, and, OR. You can figure out the exact poke code value in the following manner. Take line 10, for example. We can just type print peak 563 and 254. And here we see that the result is 0. So we can just change line 10 to read 10 poke 563 0. We could do the same with line 20. Print peak 1 and 251. This returns a value of 51, so we can just plug that into line 20. 20, poke 151. And for lines 40 and 50, we could just change them to and list it. Now you could change the rest of the pokes like this as well, but these are formatted for the sake of versatility so that you can move things around if needed. Notice that we have variable BA in line 60. I've already mentioned this earlier. This is the video bank we are working in. And in line 70, we have variable CS, which tells us which character set we are using, which is 25 out of the theoretical available 32 character sets. And variable SC tells us which screen we are using, which is 49 out of the theoretical 64 text screens possible. And actually, since all these things start with from 0, it's going to run from 0 to 31 and 0 to 63, not 1 to 64. Keep that in mind. Remember, the character set you choose and the video screen you choose must reside in the same video bank together. And you cannot place character sets, text screens, bitmap screens, and sprite shapes in areas that overlap memory locations 4096, 96 to 8191, or locations 36864 to 40959, because the video chip will always see character ROM in these locations. You can always place other data in these locations, just not data that the video chip needs to look at. This arrangement is baked into the hardware, just like how the color RAM will always reside at locations 55296 to 56295. Since we left ourselves a little room for some machine language, how about putting in a little something to speed up the copying of the character set? I rewrote the code to look a little more organized, so we're going to erase our program and paste in some new lines. I've moved the character data to line 3000 here. I've placed a machine language routine in lines 2000 to 2030. Line 10 places the machine language into memory starting at 49152, which is a very common number for most of you. We call the machine language routine in line 40, but first we tell the routine where we want the character set to be copied to, so we poke its location into register 780 up here. And the rest of the program remains similar. And here is our SYS call for the machine language program, by the way. So let's run it now, shall we? Bam! That was fast. Super fast. I mean, the program was able to load a miniature machine language program and copy the character set in like a fraction of a second, I think. So, voila. Thanks for machine language. Okay, we're done here. Let's go to the 1000 to get back to our regular non-tongue invested screen. By the way, if you want to see little tongues again here, let's isolate them. Wait. Okay, enough fun. Oh wait, we can't. I can't press return now. It's going to cause an error. Okay, now we're back. The machine language sure made things speedy, so feel free to use this machine language in your own programs. By the way, this machine language routine is relocatable, so put it wherever you want to if you'd like to use it. If you wish to copy the lowercase character set instead, just change the value of 208 in line 2010 to a value of 216. So, change this to 2016. And if you run it again, you'll see lowercase. All right. I think all of this stuff is pretty solid, but there's always a chance that I overlook something. So let me know in the comments if I have something wrong. I haven't extensively tested any of the calculations in the program. I think I have them right though, but hey. Okay, so let's switch things over to Vision Basic for a minute, and I'll show you how to do the same exact thing in Vision Basic. But before I do this, I just want to give an update on my progress in updating the software. As I've stated in prior videos, I'm working on a version 1.1 of Vision Basic, and the progress should be readily apparent. I'm currently using GeoRAM as the form of RAM expansion here in Vice. Just look next to the word XRAM here. Geo. So far, everything seems to be working perfectly fine after a gazillion bugs and crashes to get to this point. I haven't updated the version number or anything here, as nothing's been finalized, and this update probably won't be available for another month or two. I keep saying like 2 months, but I mean, I'm very bad at projections here, but I think we're really getting closer here. But I'll put out a video to announce its arrival. When I go to compile things here in a bit, you'll notice another new feature, screen blanking. I mainly added this for those who have Commodore 128s but are using them in C64 mode. Blanking the screen on these machines allows for much faster compile times. C64 compile times will also be improved by about a 5% reduction in duration, which is to be expected. The blanking feature can be turned off if desired, especially since for smaller programs you may not want the screen to blank. As I've stated before, GeoRAM access is considerably slower than RU access, but I have sped up access as fast as I can make it. And all access routines are super complicated in how they work, but you won't notice a huge difference in the compile times. GeoRAM only provides a tiny window with which to access RAM with, so it's a royal pain to move huge amounts of data through. You might notice a tiny bit of lag here and there as we resume our tutorial. So, to recreate what we did in regular BASIC, we start with this. 10 copy set 25. This copies the character set to slot 25 in memory. This here replaces several lines in the regular BASIC program. Next we type 20 vid loc 49, 49, and 25. This line replaces 3 of the lines in the regular BASIC program. The middle value of 49 is what ends up in location 648. So what you have here is screen location, where you want to print it, where you want to print screen data to, and the character set. And now we issue a char pat, oops, not a har pat, a char pat, har 4925. This line sets things up to alter the asterisk character, character 42. We need to respecify the chosen character set location of 25 when we first use this command, so that's why it might seem a little redundant, but it's necessary. Next, we use the code command to design our character with. I'll just paste in these lines. Here, you can see the 8x8 grid, right here. The code command constructs bytes using certain symbols and then sends the results to memory. The X represents bits that are turned on, and the minus sign represents bits that are turned off. You can also elect to go with the usual binary ones and zeros, but they don't contrast as well as the symbols you see here. Okay, next we'll clear the screen and display some tongues, this time in red. And then get a key press, and I'll just type that in, key press. And return the screen to normal. And then run it. Voila! 5 red tongues. Blah, 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 blah. Okay, let's list it again. If you are redefining multiple characters that are right next to each other by sequence, like the letters X, Y, and Z, for example, you only need to use the charpat command one time. Continued use of the code will start to alter subsequent characters. If you're new to the art of redefining characters, you'll probably want to retain the letters, numbers, and symbols, unless of course you are wanting to redesign the look of them. There are 256 different character shapes, though half of them are simply color inverted, aka reversed characters. Using the technique presented here is best if you are only wanting to redefine a handful of characters. Each use of the code command will take up at least 5 or 6 bytes in a compiled program, so if you end up redefining perhaps 40 or more characters, you might as well use a character editor and just load in a full character set from disk. I put the ability to create character patterns this way in Vision Basic so that you can quickly edit some characters and not have to worry about exiting the software and using a separate character editor. You can combine lines of code to take up less space though. For example, I'll insert this line here to replace line 40. And then delete 41 through 47. Oops. And list. And now not only does it take up less space in the compiled program, but it also visually takes up less space. You could use one line like this to replace the normal 8 lines of code commands, but it will be difficult to figure out what the shape is supposed to look like if you were listing your program and saw this. But combining the symbols like this will save a good number of bytes in the compiled program. Just for the fun of it, you can use the code command to put bytes in odd places. For example, if you want to change the border color to yellow, you could type the following. And press enter. And voila. Now, I know that this example is a bit pointless, but you can use the code command in this fashion to store a pattern of bits, whatever kind of pattern you want, to various memory locations. Maybe you can find a use for this. You might be able to, turn bits on and off for, one of the video registers or something. The address 2180 at the beginning of the line is where the code pointer resides. So this is a way to directly access the pointer by using let. And press the key. I need to get out of here. Alright, I think I'll stop here for the time being. I hope everyone has learned at least something new by watching this video. I want to remind people that I often, but not always, put discount codes for Vision Basic in the video description of newly released videos. The codes appear near the top and are removed after the sale is over. Before you leave, I just want to share what happened in a recent TPUG Zoom meeting. Their most recent guest was none other than the one and only Jerry Ellsworth. And it was a memorable evening that you can experience yourself via a link I'll provide in the description. If you don't know her name, then shame on you. She is co-creator of the Commodore 1, which was an enhanced version of the Commodore 64. And she was hired to bring the C64 DTV to life, which was a Commodore computer crammed into the tiny space of a joystick that could be plugged into a regular television set. It came with quite a number of classic games. In her early years, Jerry built cars for racing and actually raced as well. And she mashed together a Commodore 64 and a bass guitar. Many of you have probably seen this. How cool, right? And in recent years, she started the company Tilt 5, which sells an augmented reality gaming system. She is quite a fascinating person. I highly recommend joining the TPUG user group so that you don't miss out on stuff like this. I'll leave a bunch of links in the description for you all to check out. Okay, so that wraps things up for this video. I'll be continuing my work with Vision Basic 1.1, so make sure to subscribe so that you'll be able to stay in the loop. My next focus will be on adding and improving some commands and then getting things ready for the big reveal. As usual, I thank you all for watching my video. Please like, please share, and definitely subscribe for more similar content. And make sure to visit visionbasic.net.